What's poppin', guys? Welcome to Steady State Summary number 3, where we'll be going over weak interactions. This is easily up there with the most important content for the course, but also just to understand biochemistry in general. If you have any questions, please let me, Dr. Bernston, or any of the other TAs know. This table comes from your activity that you received in class this past week. The difference between a covalent and non-covalent bond is that in a covalent bond, the electrons are shared between the atoms. As you can see by the bond strength, these bonds are much stronger than any of the weak interactions and are typically stable in biological conditions. As you move down the chart, be sure not to note only which interactions are stronger, but why they are stronger from a chemistry standpoint. An ionic interaction, although considered strong in a vacuum, is a form of weak interaction in biochemistry. This is due to the presence of water in living systems. Water carries a polar charge that, if strong enough, will break the bonds between the ions. This is what you see when a substance dissolves. Next down the list is a hydrogen bond. Hydrogen bonds form when a hydrogen that is attached to an electronegative atom of one molecule becomes attracted to an electronegative atom of another molecule. This is commonly seen when water interacts with itself, as well as between complementary strands of DNA and in forming the tertiary structure of a protein. Hydrogen bonds occur with hydrogens bonded to oxygen, fluorine, and nitrogen. This table does a good job of describing 4 of the 5 threshold concepts of biochemistry: physical basis for interactions, thermodynamics of macromolecular structure formation, steady state, biochemical pathway dynamics, and regulation. The bottom 3 concepts each have a mention to weak interactions. This is no coincidence, and it is important to understand where the importance of weak interactions comes from in a biochemistry perspective. The physical basis of interactions mentions that structure governs function. Without proper weak interactions, many things in life cease to function correctly, such as enzymes or proteins. This plays into the thermodynamics of macromolecular structure formation, as only weak interactions that are favorable occur spontaneously under most conditions. Enthalpy and entropy of weak interactions plays into whether or not a certain interaction will be favorable. Later in the semester, this will play into biochemical pathway dynamics, steady state, and free energy. But based on this chart and what has been displayed in class, it is important to keep in mind that weak interactions play a huge role in our understanding of biochemistry. If you're ever stuck on a question on an exam, weak interactions is a good place to start. Finally, I like to touch base on the difference between hydrophilic, hydrophobic, and amphipathic molecules. A hydrophobic compound is something that does not hydrogen bond. This is typically a compound with a high density of carbon-carbon bonds or carbon-hydrogen bonds. These compounds are quite literally scared of water, and if found in a biological system, will shield themselves from interactions with water. The basis for this hydrophobic effect is that water would prefer to interact with itself. The concept like attracts like is important here. Hydrophobic molecules prefer hydrophobic regions, while hydrophilic regions prefer hydrophilic compounds. Hydrophilic compounds are substances that can hydrogen bond. As you can see in this table, many of the amino acids in the hydrophilic category have polar regions, and may even have an atom that can directly hydrogen bond. This makes these compounds' interactions with water more favorable, and these are found in regions where water is easily accessible, such as on the outside of a protein or enzyme. Amphipathic compounds are somewhere in the middle. These types of compounds have both hydrophilic and hydrophobic regions. For example, tyrosine has a large carbon ring on its side chain, but the presence of a hydroxyl group gives this amino acid a hydrophilic region as well. The most prevalent example of amphipathic molecules is the phospholipid bilayer found in cell membranes. If you have any questions about anything in this video, please let us know. I've included a link to the website where I found the threshold concepts in case you'd like to access them. Stay easy.